Hi everybody, Greyfist here. I apologize for my voice. I have just a little bit of a cold right now. But I came up with a really interesting video, and it's kind of almost an afterthought to the orbit video that I posted last. And I realized that there was one other thing that I wanted to simulate that I thought was really interesting, and that actually occurs in nature, and that is the capture of Triton by Neptune. Now, Triton's kind of an unusual moon because it's quite large, and most interestingly, it orbits retrograde to the planet. Now, what does that mean? That means that the orbit is in the reverse direction of the planet's rotation. So if the planet, for example, is rotating clockwise, Triton orbits counterclockwise. So that's kind of an unusual thing in our solar system, and for a while it was a bit of a confusion for planetary scientists. And the reason for that is when moons typically form with their planets, due to the law of conservation of angular momentum, they have this cloud of material that's sort of orbiting about its center of mass. And when the moon forms, it tends to continue rotating in the same direction as the planet, because all of the material was rotating in that direction to begin with. That's not true for Triton, and so it was kind of a mystery for quite a while. But eventually somebody proposed that Triton was actually a captured body, which means that it did not form with Neptune, but instead was captured from somewhere else in the solar system. So that's what I wanted to simulate. So on the screen here you can see that I have a hyperbola drawn. Hopefully you've had a chance to take a look at it. The bottom left-hand corner lists the equation, the semi-major axis, which is A, and the eccentricity, which is 1.1 in this particular example. We also have the directrix, which is the black line drawn horizontally across the screen. Then we have a hyperbola, and 2 points mark the focus and the semi-major axis. Now, hyperbolas can be constructed basically in two ways. There's the algebraic way, which is to simply look at the equation and then plot out the points that satisfy that equation. But the geometric way is to use the directrix and the focus. So a hyperbola is defined as the group of points for which the distance between the point and the directrix relative to the distance between the point and the focus is a constant, and that constant is the eccentricity, or 1.1 in this example. So for every point, if you take the ratio of the distance to the directrix to the distance to the focus, that ratio will be equal to E in this case, the eccentricity 1.1. Now, I didn't use that, but I felt I would be remiss to not talk about it just a little bit when discussing hyperbolas. So we also have the semi-major axis marked there, which is the point of closest approach to the origin in this particular case. In other words, it's the closest that the curve gets to the center. And obviously, in this particular case, we're ignoring the negative half of this plot, but had I plotted it, there would be a mirror image below the x-axis. There's only just a little bit of math left that I want to talk about. So we've already defined what A is, and that's the semi-major axis. Now there are two other quantities that you need to know, particularly when you're trying to plot a hyperbola using an algebraic equation as opposed to the geometrical method. From A, we can get what is usually denoted as C. C is equal to A times E, and that's actually the distance from the center of the hyperbola, or the origin in this case, to the focus. From A and C, we can get the quantity B. B squared equals C squared minus A squared. And you can see that B squared is what is actually used in plotting this using an algebraic equation. So those are just the few things that you need to know when you're trying to work with hyperbolas. Okay, so now that we've gotten through some of the basic math, we can actually get to the simulation. Now there are 4 objects in this simulation, although they don't all interact with each other, and I'll talk about that in just a moment. On the bottom left, we have the green line, which is Moon 3, and then in the top left, we have the two, Moon 1 and Moon 2, those are the red and black lines, and then in the center we have Neptune, about which everything is moving. We also have the energy of those 3 moons listed. Now, Moon 1 and Moon 2 interact with each other and with Neptune, but Moon 3 only interacts with Neptune. Basically, Moon 3 is to show you what would happen if, instead of having 2 moons of equal mass, you had a single object with twice the mass. So basically it's kind of like what happens to the center of mass as it shoots around Neptune. And of course it's been mirrored so that you can see it more easily. Now, in orbital mechanics, the energy of a body when it's on an escape trajectory, in other words, when it's not orbiting a body but is instead moving away from it, on a path that moves away from it, the energy is positive. And you can see that in the beginning of this simulation, all three objects' energies are positive and very large because they're large bodies. But as the simulation goes on, you can see that Moon 2, which is the red trajectory, actually becomes negative. And what that means is that it is actually captured now by Neptune. So it is now an orbiting body. And you can see towards the end of it that it actually does complete a full orbit. So I thought that was pretty cool. And honestly, this simulation was a lot easier than I expected it to be. I thought that I'd have to plow through the parameter space. In other words, I'd have to try a whole bunch of different initial conditions, but it only took me 3 attempts to find one setup where one of the bodies was captured. So I was really surprised, and it made me pretty excited because it would seem based on how quickly I was able to find a capturing simulation that it's not actually that difficult to capture a body. So a couple of the parameters here. We have the 2 bodies approaching Neptune at 50,000 kilometers above the center of Neptune. Now Neptune has a radius of about, I think it's 26,000 kilometers. So it passes about 25,000 kilometers or so above the surface. And the eccentricity of the hyperbola that they're on initially is 1.1. Now, an eccentricity below 1 means that it's in an elliptical orbit, or it's been captured. 1 is a parabolic orbit, which means that it will escape, but when it gets to a distance of infinity, it will be moving at 0 velocity, essentially. Now, any eccentricity greater than 1 will mean that it has velocity when it goes off to infinity. It doesn't stop, it just keeps going. So, the 2 objects start off in not a really strongly eccentric orbit, I guess you could say, but they are on an escape velocity or escape trajectory, and they're not going to be captured. And you can see that because the green moon, Moon 3, actually does escape, and it's never captured by Neptune. So once again, I thought this was really cool. I hope you enjoyed the simulation. Like it, share it, subscribe to my videos. Hopefully I'll be coming out with a bunch more soon. And thank you very much for watching.